Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the first lecture. In this lecture, we will be looking at some basic concepts related to integrated circuits. Specifically, in this lecture, we will be discussing first we will take some historical perspective of integrated circuits. Then we will be looking into the structure of integrated circuits, and we will look into some terminologies related to the fabrication of integrated circuits, and then finally we will be discussing that what is basic differences and relationship between designing and fabrication. Now, before moving to integrated circuit, let us look into a statement that was made by Charles Babbage. So, as you might be knowing that Charles Babbage is considered as the father of computers. So, in his book On the Economy of Machinery and Manufactures, there is an interesting statement. So, the statement is, the sources of excellence in the work produced by machinery depend on a principle, and is one upon which the cheapness of the article produced seems greatly to depend. So, and what is this principle? This principle alluded to is that of copying, taken in the most extensive sense, right. So, what it means, this statement means that the articles or the products or the work that is produced by machines, those are excellent and they are also cheap, and the reason for that is a principle, and that principle is copying, right. So, this statement is very much true for the industrial revolution, that when we started using machines to make products, and it is also very much relevant to digital revolution that we are seeing today, right. So, in the digital revolution, or the digital revolution is enabled by chips or integrated circuits, and how we can manufacture such complicated complex integrated circuit and also keep their cost very low. It is the reason for that is that we have actually mastered the technique of copying an integrated circuit. Now, what do we mean by copying an integrated circuit? We will see in today's lecture. So, let us first take an historical perspective of VLSI. Now, if we consider any electronic circuit, an electronic circuit consists of some active components and some passive components, right. Active components like say transistors and diodes, and passive components like resistance, capacitance and inductors and so on, right. So, any given circuit consists of these kind of circuit elements or components. So, in earlier days what we used to do is that we used to create a system or electronic system by adding discrete components or connecting discrete components over the board, right. We used to have say transistors as discrete component, resistor as discrete component, and we used to realize the system by connecting them at the top level, right. Now, as the complexity of this electronic circuit goes on increasing, then this method of putting together discrete components and realizing a system becomes very expensive, it becomes time consuming also, and it becomes unreliable and error prone, right. So, to handle these situations or the problem of integrating together or putting together discrete components and realizing a system, a new technology was invented in 1960s. And what was that new technology? The new technology was integrated circuit. Now, what is an integrated circuit and how is it different from putting together discrete components? So, an integrated circuit is basically a monolithic silicon chip which contains several components. And what do we mean by monolithic silicon chip? It means that the silicon chip or the substrate or the silicon that we use, it is consisting of only single crystal of silicon. And over that single crystal of silicon, we are integrating multiple components like transistors, diodes, resistors, and so on. It is not that we are putting together different components and putting them, combining or adding them together. On the silicon substrate, using some technology, we are growing transistors or making transistors, diodes, resistors, and so on. And as a result, the complete system is one piece of monolithic silicon chip, right? And that is what is known as integrated circuit. And how can we fabricate or make this integrated circuit? We can make this integrated circuit with the help of a technology which is known as IC technology, right? So, this IC technology has actually was enabled, or it was invented in 1960s, and at that time lots of inventions were made, and also discoveries of, say, good properties of silicon dioxides and those kind of, and the interface of silicon and silicon dioxide, those were discovered and those things were utilized in the integrated circuit, right. So, over the last 50 years or so, lot of inventions and discoveries has been made in IC technology, as a result of which we can realize very complicated chips, right. And among these IC technologies or the various inventions and discoveries, one of the technique is what is known as photolithography. And this is the basic technique which allows us to copy integrated circuit, right. So, we will be looking into photolithography in more detail in subsequent slides, and this is a key thing that we should understand, and that the photolithography is the key technology which has enabled IC technology, and this IC technology has enabled making complicated circuits, and that has basically spurred the digital revolution that we are witnessing. Now, when IC technology was invented, say in 1960s, at that time a few components could be put together on a monolithic silicon chip, maybe say tens of them, and that was small scale integration. And with time this technology matured and we could add more components, say thousands of components, and we moved into then large scale integration, and then we moved to, say, very large scale integration, where at this point of time we can have, say, millions or billions of components together, put together inside our integrated circuit, right. So, when in 1960s, when this technology was still being developed, Moore made a famous prediction, right. At that point of time, even when 1960s, when only tens of components could be combined together, at that time Moore could observe the trend of increasing integration, and he made a famous prediction, and which is now known as Moore's law, right. And what was that prediction? So, the prediction was that the number of components in an IC realized at minimum cost will double every year, right. So, it is doubling every year, and later on seeing on that basis, or observing the trends, he modified his statement in 1975, and he said that it will be double every 2 years, right. But this is a kind of exponential relationship, right. With time the things is doubling, right. And this is, and surprisingly, this prediction which was made in 1960s, that has been true till now, and we are seeing an increasing level of integration of integrated circuit, meaning that we are able to pack more and more components and still maintain the cost or the cheapness of the article to a level where a common man can afford these mobiles and laptops and other sophisticated equipment, right. Now, how can we pack so many transistors in our integrated circuit? So, the basic reason is that with time, as the technology has advanced, we are able to shrink the size of the transistors, right. We can make smaller and smaller transistors. For example, in the earlier days, there was a 90 nanometer technology, right, and then it gradually advanced to, say, 65 nanometer, 45 nanometer, 32 nanometer, and so on, right. So, these technology names basically in some manner denote the size of the transistors, and when these names have smaller number, it basically means that the sizes of the transistors are basically becoming smaller and smaller, right. And when we make the sizes of the transistor smaller, what gain do we get, right? So we get gain in almost all the parameters, meaning that the speed increases, the energy efficiency increases, meaning that given a computation, how much energy is required to do that computation. That energy is also reducing with technology advancement, and the cost per transistor is also reducing, right. With time, the cost per transistor has been reducing, and all these things are so much favorable that the technology has gradually moved in a direction that the sizes of the transistor goes on decreasing, right. Now, of course, there are lots of benefits of shrinking of the transistors or miniaturization of transistor or advancement in technology. But what is the downside? The downside is that the design becomes more complicated, right. As we add more and more transistors in a given area, so the number of transistors that a designer need to now handle is much larger, right. And therefore, designing an IC becomes more complicated and challenging. And in this course, throughout this course, we will be looking at this challenge and how we can address this challenge of increasing design complexities as the technology advances. Now, let us look into the structure of an integrated circuit, like how does an integrated circuit look like now. So, first let us take a very simple electronic circuit, say CMOS inverter, right. This is a very simple integrated circuit. We have say PMOS, right, PMOS or P MOSFET and an N MOSFET, which are connected in complementary manner, and this is nothing but a logical AND inverter, right, or NOT gate. So, when we apply 0, we get 1 at the output. If we apply 1 at input, we get 0 at the output, right. See, this is a very simple circuit, right. Now, corresponding to this, how will the integrated circuit look like, right. So, I am giving you an one of the way in which this integrated circuit can be realized, right. So, this is a simple inverter, right. Now, it looks very complicated. So, do not worry about the complicacy of this integrated circuit. We are not going in details, or in this course we will not go into details of the fabrication of this integrated circuit. But there are some salient features of the integrated circuit which we must understand, and because that is very much relevant to the designing of integrated circuit, which is the primary focus of this course. So, what are some of the salient features of the integrated circuit? So, the first thing is that the integrated circuit is composed of multiple layers. So, in the figure that I have shown here of integrated circuit, what we have done is that there is an integrated circuit, we have taken a cross sectional section, vertical cross section, and this is representing a vertical cross section of the integrated circuit. Now, in this integrated circuit, there are many layers of entities. For example, at the bottom there are diffusion layer, then there are implant layer, and there are metal layers. So, here we have shown only 2 layers of metal 1 and metal 2, right. There can be more than 2 layers of metals, right. So, the bottom of this integrated circuit, that is the entities below this level, that the level that I have shown here, right. In this region, we have devices meaning transistors, diodes, and those kind of things, right. For example, this is a PMOS and this is an NMOS. So, devices sit on the lower layer of the integrated circuit, and above the devices we have the interconnects meaning the metal layers which are connecting, say, one device to another. For example, this NMOS, PMOS and NMOS are connected together, and this connection can be made using interconnect metals or some other kind of interconnects like polysilicon and so on, right. So, on the bottom we have the devices, above this we have layers of metals, right, and it can be more than 10 layers of metal. In this figure I am just showing 2 layers of metal, like metal 1 and metal 2. There can be in advanced integrated circuit that we use currently, we have typically more than 10 layers of metals, right? And these metal layers are connected among them together using another kind of metal layer which is known as via layer, right. So, if you are not able to understand this figure, it is perfectly fine, right. So, we are not going into the structure of integrated circuit in detail in this course, but a few important things that we can extract or understand from this figure is that an integrated circuit consists of multiple layers of entities. For example, there will be layers of devices composed of say diffusion layer, implant layer and so on. Above this there will be layers of metals which are connected and so on, right. Now, a very relevant question arises that why we realize integrated circuit in terms of layers? Why not a flat thing? Why we have so many layers of metals, sometimes 10 layers of metals, right. So, let me explain this question with the help of an example, right. So, consider this case that we have say two terminals A1 and A2, right, and there is another two terminals B1 and B2. Now, we want to connect B1 to B2 and A1 to A2, right. With these two are separate connections. So, we need to connect to B1 to B2 and A1 to A2, but they should not short, those connections should not short. And again we are given a constraint that we cannot move out of this bounding box, this square that we have shown, the connection cannot go out of it. And I give you another third constraint that connections cannot move out of the plane of the screen or the paper that we are showing, right, it has to remain in the same plane. Now, given all these constraints, can we find a connection? The answer is no. In whatever way we make a connection, it will always short. For example, we connect B1 to B2 and A1 to A2, there is a short circuit at this point, right. This is a short circuit and therefore, it is not a valid connection. So, if we are constrained to remain in one plane, right, and the area is also constrained that we cannot go out of the area, given area, then making or finding a feasible solution is very difficult, and in this case it is impossible, right, impossible. So, but what happens when the constraint of wires being in the same plane is removed? If we say that okay, now you can move, you can connect in different layers of metals, right, or if in different planes these wires can run. Now, can we make the connection? The answer is yes. So, let us look into how we can make a connection, right. So, we can make a connection as shown in this figure, right. So, this is the top level view, this is the top level view, and these two are side level view, side views. So, what this side view is that we are looking in from this side, right, we are looking from this side. Then we can see that A1 and A2 is connected in one plane, right, through this connection, and the connection between B1 and B2 is in a different plane, it is in this plane, right. So, if we take a view on this side, from this side view from this side, then we can see that B1 and B2 is connected and it is above this, right. So, if we remove the constraint that the connection should be in the same plane, then we are able to find a feasible solution. So, what is in this case, what is this feasible solution? So, the feasible solution is that the connection starts from A1, it moves up, right, goes in one plane, then goes down to A2, and from B1 what it happens, it goes again to some other level, right, to a different plane, make connection and then goes runs in parallelly and then goes down to connect to B2. So, these two connections are running in two different planes and therefore, they are not shorting, right. So, what is this problem telling us, right, or what we can infer from this example? We can infer that if we remove the constraint of making wires in the same plane, or we allow the wire to run in different planes, then making connections become easier in a given area, right. And that is what the primary motivation of making integrated circuit in various layers. We have say 10 layers of metal, then very complicated connections can also be made by running in different planes, right, and and therefore the structure of integrated circuit is in the form of layers, right. Now, different layers of these interconnections and also for devices, those are made using a technology which is known as photolithography, right. Now, how these connections are needs to be made, that is defined by something what is known as mask, and that using that mask and the photolithography technique, we can copy that connection into multiple integrated circuit. So, now let us look into that what is photolithography and how we are able to make patterns on the silicon wafer using photolithography as we design, right. So, what is photolithography? Photolithography is a process of transferring geometric shapes that are defined on a mask to the surface of the silicon, right. Now, what is a mask, right? So, photolithography basically transfers features from the mask to the silicon's wafer, right. So, before going into the details of photolithography step, let us understand what is this mask and what its use is, right. So, mask is basically a transparent plate, it may be of say glass, over which there are some opaque regions. For example, this is the top level view of a mask. So, we have this mask is made of say glass, which is a transparent material, and in this transparent material we have opaque regions, right. These opaque regions may be by deposited chromium and so on, right. So, we have some pattern on the glass plate, some opaque region, some transparent region, right. And these masks are also known as photo mask or reticles, right. And in when we fabricate integrated circuit, what we do is that whatever the pattern is there on the mask, that is where there is an opaque region, where there is a transparent region, we want to get similar pattern on the wafer, right, and we get it using the process known as photolithography, right. Now, as I described earlier, that integrated circuit consists of multiple layers of different types, and for each layer when we design our circuit, we have different patterns and we will have different masks for each layer, and we transfer the pattern which is there on the mask onto the wafer layer wise. For each layer we will have mask, and on each mask we will have the pattern, and we want that pattern to be transferred to the integrated circuit, and we do that transfer of pattern using this task known as photolithography. So, now let us look into that how photolithography is done. Suppose we have a substrate which is silicon wafer, right, over which there is a deposited film. This deposited film may be say silicon dioxide, silicon nitride, or other kind of deposited film, and on this we want to pattern this deposited film. Then how can we proceed? So, first what we do is that on this deposited film we put photoresist. What is a photoresist? Photoresist is a chemical which is sensitive to light, meaning that wherever the light falls on photoresist, this property changes, right. Now, photoresist is typically a liquid kind of thing. So, what we do is that over the deposited film we drop photoresist, and then using spinning of the wafer we make it a uniform coating of liquid photoresist over the wafer, and then we do a kind of baking which solidifies this photoresist, right. So, once we have applied a uniform layer of photoresist over the deposited film, then what we do? Then we expose the photoresist to the light, right, and we expose this photoresist to the light through the mask, right. Now, remember that the mask contains the pattern, right, the mask contains the pattern where an opaque region, transparent region, and so on. So, the region where it is transparent, light will go and it will interact with photoresist and the property of photoresist will change wherever there is a transparent region. And wherever there is a opaque region, light will be blocked by the mask and the property of photoresist will not change, right. So, the pattern that was there on the mask, now that gets transferred to the photoresist, right, because the light has fallen through the mask and light has changed the property of photoresist wherever it has fallen, and wherever it has not fallen, the property remains the same. So, this phase is known as the exposure phase. Then what we do is that we go to the next task, which is known as development. We take the wafer and put it in a developer solution. Now, when the developer solution is a solution which interacts with photoresist which has been exposed with the light, right. So, the region where the light had fallen, that will be reacted with this developer solution and that will be removed out, right. So, now we have on the photoresist, we have a pattern of hollows and where the photoresist remains intact, right, and that pattern is defined as it was on the mask, right. So, in the development, after the development stage, we have regions where the photoresist have got removed and region where the photoresist is as it is, right. Then what we do is that we subject this wafer to a step which is known as etching. So, in etching, what we do is that we expose the wafer to a special type of chemical which is known as etchant, which reacts with the deposited film, but does not react with the photoresist. Now, if there is that kind of chemical, then only the deposited film where the photoresist was removed, that will get removed, right. So, we will have a pattern here, right, on the deposited film, and wherever there was a photoresist, that region will be actually resisting the etching, right, and therefore, in this after etching we will have a pattern on the deposited film, right. And then what we do is that we remove the photoresist and we have got the pattern that was on the mask, right. The pattern that was on the mask, we have got that pattern on the deposited film, right. That is what the task was of photolithography. So, we got the pattern which was there on the mask to the wafer, right. Now, when we do designing, right, when we design our circuit, what we finally do is that we get a pattern of that should be on the mask, right, and once we have created this mask, we can do photolithography using the same mask thousands of times, right, and therefore, we are able to copy the integrated circuit. So, that how the integrated circuit should behave, that is defined by the mask, right, and that we have done once. Once we have got the mask, we replicate that or we copy that integrated circuit multiple times by carrying out photolithography separately for each of the wafers, right. So, this is basically what I meant to say by the art of copying integrated circuit, and the crux of this is basically the photolithography step. Now, let us look into some terminologies related to IC fabrication. So, these terminologies will be used again and again in the course, and therefore, you should be familiar with it. Now, what is a silicon wafer, right? So, a silicon wafer is a thin slice of silicon that serves as a substrate for an integrated circuit. So, this is the picture of a wafer, right. So, typically it is of 300 diameter, right, and on this silicon wafer basically we create integrated circuit, right. So, this silicon wafer is a single crystal of silicon, right, and this is a thin slice of silicon of diameter typically of 300 size, and on this we will be creating our integrated circuit. Now, a basic question comes that how do we get this monolithic or crystalline silicon wafer? We get it using what is known as silicon ingots. And what are silicon ingots? Silicon ingots are massive cylindrical single crystal of silicon. So, this figure is showing what is a silicon ingot. It is a massive cylinder of silicon, and it is just a single crystal of silicon, right, a single crystal of silicon which is almost defect free. It is very less defect will be there in this kind of silicon, right. And using this silicon ingots, we make silicon wafers. And then the question comes that how do we get these silicon ingots? So, we get this silicon ingots using a process known as CZ process, in which what we do is that we have a single crystal of silicon which is dipped inside a molten silicon which is at 1425 degrees Celsius. So, there is a molten silicon which is at say 1425 degrees Celsius, and in that we had dipped a crystal of single crystal or seed crystal of silicon and slowly pull it up, right. When it slowly pull it up, then silicon crystallizes around that seed crystal, and gradually this massive cylindrical form of silicon ingots are formed. So, this is very simplistic description of how silicon ingots are made, but it describes fairly well that how silicon ingots can be prepared, right, but the technology is far more complicated. Now, once we have the silicon ingots, which is a perfect or which is a nearly perfect single crystal of silicon, then we slice out silicon wafer out of it, and we get silicon wafer on which we make our circuit. Now, once we have say silicon wafer, then on a single silicon wafer we create multiple integrated circuit. It is not that only one integrated circuit is made on a single on a silicon wafer. We create multiple integrated circuit on the silicon wafer, and this multiple these integrated circuits are known as dies. So, the slices of silicon wafer containing the complete circuit are called dies. So, this is a silicon wafer, and in this silicon wafer, this is small square which is blackened square that is shown here. This is a single, this is a die, right, and this die contains the complete circuit or complete integrated circuit, right. So, the hundreds of rectangular shaped integrated circuits are fabricated on a single silicon wafer. So, when we do the fabrication on a silicon wafer, this is a silicon wafer, right. On this silicon wafer, we will have hundreds of each square that is shown in this figure is separate silicon die or die, right, and each die contains self-contained circuit, right. Now, these dies are, once it is fabricated, once they are fabricated, these dies are sliced out from the silicon wafers after fabrication and testing. One important point to note here is that when we fabricate many dies on a single wafer of silicon, then some of the dies may be having defects also, right. So, one of the important things in manufacturing of integrated circuit is to consider that how we can make the percentage of good die or defect free die among all the dies fabricated on the wafer. So, that percentage is known as yield, and typically we try to make yield as high as possible in a fabrication technology. So, once we have fabricated hundreds of dies on a wafer, then we test each die, and then we slice out these dies from the wafer. For example, we slice out this die, then we get this is the figure or representation of a single die of a single die that is fabricated on the silicon wafer. Now, this die will contains millions of transistors, right, depending on the functionality of the circuit or the integrated circuit. This die, this is a die, right, and this die can contain millions or billions of transistors, right. Now, once we have sliced out these dies, then the next step is basically packaging. So, after dies are sliced, they are encapsulated into a supporting case which are known as package, right. These are known as package for, and these package are used for protection against physical and chemical damage. So, once these dies are sliced out from the wafer, then they are encapsulated inside the package, and once these are encapsulated and ready, then what we get is a chip, right. So, what we get a chip which goes to the market or gets integrated into a system and then goes to the end user. So, to summarize what we in the fabrication of integrated circuit, what we do is that we start with a silicon ingot, a massive cylinder of single crystal of silicon, right. From silicon ingot we slice out get silicon wafers, right. On a silicon wafer we have hundreds of dies, and each die will contain say millions of transistors, and as each separate die contains a self-contained circuit, and then we take the die and package it, and once we package this die, this goes to the system, making the system, or goes to the market for sale, and then that entity is basically known as chip, right. So, you should be able to understand the difference between wafer, die, chip and silicon ingot. Now, another thing that you should understand right at the outset of this course is that what is the difference between designing and fabrication. There are differences, but there are also relationships. So, let us look into what is the differences or what are the differences between designing and fabrication. So, what is designing? Designing is basically determining the parameters and composition of a circuit that can achieve the desired functionality, right. So, in designing step we are determining the parameters of the various components and the entities. For example, once we are designing the layout, then we are saying that what would be the size of the transistor, where they should be placed on the layout, how they should be connected and so on. That is the design aspect. Designing means that determining the parameters of our circuit and so on, right. So, the designing is once we start with the functionality, and the designing step ends once we get the layout, right. We get the layout, meaning that where the transistors are there, how they are connected and so on, and this layout is basically containing all the information which is required to make different masks for lithography that we have just seen, right. So, the design step ends once we have made the layout and a mask can be fabricated or made out of it, right. Then comes, after the designing part comes the fabrication part. And what is fabrication? Fabrication involves actual creation of integrated circuit for a given design. So, in fabrication we are not changing the parameters of the circuit that is given to us. We start with the given parameters and then produce the integrated circuit or physical integrated circuit, and typically in bulk, right. So, this part is basically copying of the integrated circuit. So, the designing part makes that decides what should be the parameters of the circuit. When that is decided, then fabrication process basically replicates it for millions of entities, and we get millions of products, right. And actually over the years, last 50 years, we have mastered this technique of fabricating integrated circuits, and therefore the cost of the integrated circuit has really come down. So, we are the cost per transistor, it is several orders of magnitude lower than what it was say 50 years ago, right. Now, where do we fabricate or do the fabrication of integrated circuit? So, we do the fabrication in semiconductor foundries. So, semiconductor manufacturing plant where fabrication of integrated circuit is done, that is known as a semiconductor foundry, right. Now, an important point to understand that this setting up these semiconductor foundries is very expensive. It requires huge capital. For example, in say 5 to 10 billion dollars, right, to set up one fabrication plant. That is what that is how expensive setting up a fabrication plant or foundry is, right. So, why this cost is so high? The cost is so high because we need to have a very controlled environment for fabrication, which are basically known as clean rooms, and we need lots of sophisticated equipments to manufacture these transistors and these circuits at the nanoscale dimensions. So, therefore, the investment required to set up a semiconductor foundry is really high in billions of dollars. And added to that, there is another downside of these semiconductor foundries. The downside is that it has got a semiconductor foundry has got a shelf life, meaning that it gets outdated after say 5 to 10 years, right. And therefore, as an entrepreneur, if you want to set up semiconductor foundry, it means that you have to recover the cost of the investment in 5 to 10 billion dollars in a limited span of time, say 5 to 10 years. And therefore, and also as an entrepreneur, you will want to make profit out of it. So, to make profit in a limited time frame, what we need is basically that these foundries should be running at maximum capacity or full potential most of the time. So, the business of semiconductor foundry is sustainable only when the facilities of foundries are utilized to close to full potential, right. And because of this constraint, various forms of semiconductor ecosystem has evolved in last 25 years. So, let us look into these ecosystems, because when you go into designing, you will be basically working in that ecosystem, and if you understand this ecosystem, then you can basically appreciate that how the things are being designed, how they are manufactured and so on. So, let us look into this semiconductor ecosystem very briefly, right. So, in this in the semiconductor industry, a business model has developed which is known as fabless design companies, right. So, there are many design companies which are just doing designing, they are not doing fabrication, they are outsourcing the fabrication to some other companies. For example, companies like say Qualcomm, Nvidia and so on, they only do designing and fabrication is outsourced. So, this business model is very lucrative because these companies need not set up expensive fabs, right, they need not do a high investment, and therefore, they do not require a huge amount of money to set up and maintain costly foundries, and therefore, this business model is sustainable, right. And there is another business model which is of merchant foundries. And what are these merchant foundries? These merchant foundries only do fabrication, right. So, they do fabrication for different design houses and so on. And as a result, what it happens is that it can draw lot of business from multiple entities, right. So, these are merchant foundries, for example, TSMC, UMC and Global Foundries. These are doing the fabrication for other companies, for example, these fabless design companies. And since there are lots of fabless design companies, business comes to merchant foundries regularly, and these merchant foundries can run to the full potential, and therefore, it can make profit in its foundry business. And another kind of business model is of integrated device manufacturers. So, in these companies, what happens is that designing and fabrication is done in the same company, and they become more efficient and cost effective due to control over the entire design step and fabrication step, and therefore, they can also succeed. So, example of integrated device manufacturers are Intel and Samsung, right. These are a few examples, right. Now, we saw that typically what we do is that the designing part is segregated from the fabrication part, right. But are these two tasks independent? The answer is no, because while designing, we must know that finally what will be the attributes of the transistor, for example, delay and so on, because we need to take into consideration the consideration of the properties or attributes of the transistor during the design phase. And these properties are decided by how we fabricate things. It will be different for different foundries, right? And therefore, designing and fabrication, though we do it separately, they are not separate processes. They need to take information from each other, right? So, the design and fabrication, those are related tasks, and to maintain consistency between designing and the fabrication, we must share information, right? What we do is that the foundry, depending on how it is fabricating transistor, what material it is using, and what are the process parameters and so on, they do some characterization and they share what is known as PDK or process design kit with the design team, right. So, the foundry shares PDK to the design team, and this PDK contains this PDK contains information of the, say, the attributes of the transistor, what will be the current and the given circuit condition and so on. So, the properties of the transistors and devices will be defined in this PDK, and also there will be some rules which foundry enforces for the design, and those rules are basically encoded and kept inside this PDK. And as a designer, when we do designing, we must be aware of those design rules, and while designing our circuit, we must adhere to them or follow those rules. If we follow those rules, then the foundry will guarantee us that the yield of the manufacturer of the integrated circuit, meaning that how much percentage of the circuit will be good or defect free, that will be such that this designing and making of the chip will become profitable, right. So, the foundry and the fabrication and the designing, those are separate process, but to make them consistent, we have some entities like process design kit, where the foundry shares the information with the design team follows the information or adheres to the rules that are defined by the foundry and makes the circuit, and then the circuit goes to the foundry, and the foundry can fabricate that circuit with a good yield, and this venture can be basically successful. So, if you want to look into these topics more deeply, then you can refer to these textbooks. Now, to summarize in this lecture, what we have done is that we have taken an historical perspective of VLSI. We looked into the structure of VLSI, and then we looked into a task which is known as photolithography, and how photolithography can be used to replicate the features that is on the mask on the wafer, right. And so, this is the key step which allows us to copy integrated circuit and make very complicated integrated circuit and make it available to the consumer very cheaply. So, in the next lecture, we will be looking into some more basic concepts related to integrated circuit. Thank you very much.